What if the universe has already decided humanity's fate before we even understood the question? What if the vast emptiness separating us from our nearest stellar neighbor isn't just empty space, but an unbridgeable gulf that fundamentally rewrites everything we've imagined about human destiny among the stars? Tonight, we venture into a territory that defies both our romantic visions of space exploration and our stubborn human optimism. We're going to confront a simple yet devastating reality: Proxima Centauri, the closest star system to Earth, a mere 4.24 light-years away, might as well exist in another universe entirely when it comes to human travel. Not because the science is impossible, not because the engineering can't be solved, but because the numbers that govern our universe have created a prison so subtle, so mathematically elegant, that we only now are beginning to understand its bars. The closest star system to us sits 25 trillion miles away. Let that number breathe for a moment. If you could somehow travel at the speed of light itself, something nothing with mass can achieve, it would still take you over 4 years of continuous flight to reach it. 4 years in an absolute vacuum, moving at 186,000 miles per second. 4 years of eternal night. 4 years where messages from home, traveling at the same speed you are, would arrive so delayed that any attempt at conversation becomes absurd. But what if our current spacecraft could reach Proxima Centauri? What if we accelerated the fastest human-made object ever built, the Parker Solar Probe, currently traveling at 120 miles per second in the direction of Proxima Centauri right now? Even at this incomprehensible speed, the journey would consume 73,000 years. 73,000 years. That's not a voyage. That's an exile that would outlast recorded human civilization by an order of magnitude most minds cannot actually grasp. And yet, what if this realization isn't the end of the story? What if understanding just how far away Proxima Centauri really is, both in distance and in the resources required to reach it, opens doors to something far more profound? What if the mathematics of stellar distances reveals something about the universe's design, about the nature of cosmic isolation, and about whether the silence of the cosmos is actually a warning we've been too distracted to read? This is the paradox we're exploring tonight. The universe has placed its hand on our shoulder and asked us a question in the language of numbers and physics. Is interstellar travel the future of humanity? Or is it the most seductive lie we've ever told ourselves? The distance to Proxima Centauri isn't just a challenge to our engineering. It's a test of our willingness to confront uncomfortable truths. Before we dive deeper into this cosmic puzzle, if you're fascinated by the mysteries of space, the limits of human potential, and the hard science behind our wildest dreams, make sure to hit that subscribe button and ring the notification bell. Drop a comment below telling me what time it is where you're watching from. I love seeing our global community come together from Earth, all of us standing on this one island of rocky habitability, contemplating the stars beyond. And if you appreciate the deep research that goes into examining these cosmic mysteries, a like genuinely helps the channel grow and ensures more of you see this content. Let's continue our journey into the sobering mathematics of interstellar distance. Let's start with what authorities and institutions actually tell us. The European Space Agency and every serious space agency has the same official position. Interstellar travel is theoretically possible, but practically centuries or perhaps millennia away from implementation. They're not being poetic. They're being precise. The Parker Solar Probe, launched by NASA in 2018, holds the current record as humanity's fastest spacecraft. It's traveling at approximately 120 miles per second relative to the Sun. This is a probe no humans aboard, no life support systems, no scientific instruments that need to survive intact. It's essentially an armored vessel of technology designed for speed and nothing else. It will never reach another star. It's not aimed at any star. If we were to aim it at Proxima Centauri today, it would arrive in roughly 73,000 years. To put 73,000 years in perspective, 73,000 years ago, humans existed, but they hadn't yet developed agriculture. They hadn't formed permanent settlements. Writing didn't exist. Mathematics didn't exist. Everything we recognize as human civilization has emerged in a period of time shorter than the journey a spacecraft would take to reach our nearest stellar neighbor. Official reassurance comes in the form of theoretical frameworks. Scientists point to concepts like solar sails, which could theoretically propel spacecraft using photons from the sun. The Breakthrough Starshot initiative, funded by billionaire Yuri Milner, proposes sending gram-scale probes to Proxima Centauri powered by enormous Earth-based lasers. The proposed journey time, 20 to 30 years for a tiny probe weighing mere grams. For comparison, the Voyager 1 spacecraft weighs approximately 730 kilograms and has taken over 45 years to travel approximately 24 billion kilometers, still billions of miles away from even beginning to approach another star system. NASA and ESA have published roadmaps suggesting that crewed missions beyond the solar system might be possible within 200 to 300 years, assuming sustained technological progress and resources. This is important. They're not saying it's impossible. They're saying it's impractical within any time frame relevant to current human civilization. The safety reassurances come from multiple angles. First, there's the reassurance that Proxima Centauri isn't going anywhere. It's a dim red dwarf star, burning its fuel slowly, likely to remain stable for trillions of years. There's the reassurance that if we ever did develop the technology to reach it, the star system itself presents no additional threat. Small red dwarf surrounded by several planets, one of which, Proxima Centauri b, may have liquid water on its surface. An oasis in cosmic terms. But here's where we begin to plant the seeds of deeper questions. These reassurances assume two things: that human civilization will remain interested in space exploration for centuries, and that resources will continue to be devoted to increasingly ambitious projects despite diminishing immediate return on investment. History suggests this is optimistic. Consider that the Apollo program represented 0.5% of the US federal budget at its peak. Sending just a handful of humans to the moon, 240,000 miles away, consumed roughly the equivalent of $2 trillion in today's money, spread across a single decade. And this was when the competition with the Soviet Union drove national urgency. current symbol of international space cooperation, costs approximately $150 billion over 30 years of operation, and its orbit is just 250 miles above Earth. What would it cost to develop technology to move a crew of humans at sufficient velocity to reach Proxima Centauri with all necessary life support, radiation shielding, and redundant systems in less than a century? Conservative estimates from physicists exceed trillions of dollars. This is before inflation, before unforeseen complications, before the inevitable technological deadends and false starts. Yet, despite these financial and practical obstacles, what shadows might lurk beneath the reassuring words of official statements? Despite their assurances that we'll figure it out eventually, NASA's own scientists acknowledge something rarely stated so plainly. The closest star might as well be infinitely far away given the constraints of human physiology and our current technological trajectory. The average human lifespan is approximately 80 years. A crude journey to Proxima Centauri, even at optimistic assumptions about future propulsion, would require multiple generations to complete. This creates profound psychological, social, and biological challenges that pure physics doesn't address. We're not just talking about engineering a better spacecraft. We're talking about creating a civilization in space that could sustain itself, reproduce, evolve, and remain committed to a mission whose completion they will never witness. This bears repeating. Even if we solve the engineering problem, we still face the biological reality that no single human alive in any generation aboard such a vessel would ever see their destination reached. They would live, work, have children, age, and die with Proxima Centauri still years, perhaps decades away. So are we actually prevented from reaching the closest star? Or are we simply prevented by the collision of mathematics and human nature? Despite official assurances of eventual capability, a darker pattern emerges. Every serious analysis of interstellar travel reveals that the obstacles aren't primarily technological. They're existential. Let's talk about the scale in a way that actually allows the human mind to grasp it, even if just barely. The Sun is approximately 93 million miles from Earth. This distance is called an astronomical unit, or O. It's the baseline measurement for discussing distances within our solar system. We've populated our solar system, at least conceptually, in our most ambitious plans with spacecraft out to Saturn's moons. With rovers on Mars, we treat distances up to about 30 astronomical units as nearby space exploration. Everything within this radius feels almost local in cosmic terms. Proxima Centauri is 40,000 times farther away than the Sun. Let me restate that, 40,000 times farther. If you were to drive a car at highway speeds toward the Sun, it would take you roughly 200 years of continuous driving to reach it. The same car, driving toward Proxima Centauri, would reach its destination after 1.4 billion years of driving, roughly the age of life on Earth. This comparison breaks down because obviously you can't drive in space, but the number itself refuses to be ignored. In kilometers, Proxima Centauri is 40.1 trillion kilometers away. The Parker Solar Probe, traveling at 120 miles per second, 190 kilometers per second, would require approximately 210 million seconds to reach it. That's approximately 6,700 years using our fastest spacecraft's velocity. Assuming that spacecraft never slowed down and that it could somehow maintain that velocity indefinitely in the interstellar medium. But here's where the numbers get truly staggering. The Parker Solar Probe achieves its incredible speed by using gravity assists from the Sun. It swings close to the Sun, is flung away at higher velocity, then swings close again, accumulating speed with each pass. To maintain 120 miles per second in interstellar space, far from the Sun's gravity well, a spacecraft would need to carry fuel with its vast amounts of fuel. The Tsiolkovsky rocket equation, the fundamental mathematics of space travel, describes how fuel consumption grows exponentially with desired velocity. To accelerate a spacecraft to even 1/10 the speed of light, roughly 18,600 miles per second, a crewed vessel would require fuel that weighs 10 to 100 times the spacecraft itself, and this is for acceleration. You also need fuel to decelerate, or you'll simply crash into the star system at civilization-ending velocity. The Voyager probes, built in the 1970s and still operating today, are humanity's most successful interstellar messengers. After 45 years, they're traveling at roughly 11 miles per second, about 10 times slower than the Parker Solar Probe. They will take roughly 40,000 years to reach Proxima Centauri. By comparison, written human history spans only 5,000 years. The Voyagers are older than every empire, every war, every human achievement in recorded time relative to the distance they'll travel before reaching another star. Consider the comparison in a different way. Light travels from the Sun to Earth in 8 minutes. Light travels from the Sun to the edge of the solar system in roughly 5.5 hours. Light travels from the Sun to Proxima Centauri in 4.24 years. At the speed of light itself, the universal speed limit, the fastest anything can possibly travel lit, still takes over 4 years. Nothing with mass can reach that speed. Anything we could possibly build, piloted, would take considerably longer. If we were somehow able to develop a spacecraft capable of traveling at 10% the speed of light, 0.1 ca theoretical achievement that would represent more technological progress than all previous human history combined. The journey would take 42 years. It's a reasonable human lifetime for a spacecraft crew. But here's the problem. We have no propulsion technology on any horizon that could approach 0.1 c. The most optimistic theoretical propulsion antimatter engines, or advanced fusion rockets, might be capable of reaching 5 to 10% the speed of light under favorable conditions. But these are purely theoretical. They don't exist. They don't work. The physics says it's possible. Engineering says it's not. Let's engage in a thought experiment. Imagine we declared a global initiative equivalent to the Manhattan Project, but more so. We committed every technological resource on Earth to building an interstellar vessel. We spent trillions of dollars. We gathered the best physicists, engineers, and materials scientists. We solved propulsion problems that currently have no solution. We somehow achieved acceleration to 5% the speed of light. The journey would take 85 years. During that journey, onboard life support would need to function perfectly for the entire voyage. No catastrophic failures. No conflicts that destabilize the social structure of a contained society. No plagues. No accidents. Perfect fidelity of all biological and mechanical systems across nearly a century. And this assumes we've solved problems we haven't begun to solve yet. Radiation shielding for deep space remains theoretical. The psychological effects of being enclosed in a tiny vessel for 8 decades remain unresearched in human subjects. Multi-generational management of crew aboard a single vessel with no possibility of rescue remains untested. But what if these numbers hide something more? What if the real worst case has nothing to do with the physics of distance itself? Among the millions of stars visible from Earth, Proxima Centauri holds a unique place in human imagination, but not for the reasons you might think. It's not the closest star because it's special. It's special precisely because it's the closest star, and everything about it forces us to confront uncomfortable truths. Proxima Centauri is a red dwarf star. It's small, dim, and ancient. If you tried to observe it without a telescope, even knowing exactly where to look, you wouldn't see it. It's invisible to the human eye. It was discovered in 1915 by Robert Innes, but only with photographic plates and careful measurement. For most of human history, we didn't even know our nearest stellar neighbor existed. The star itself is unusual. It's prone to flare activity, sudden, violent eruptions of radiation that can temporarily increase its brightness by a factor of 2 or 3. For a habitable world orbiting such a star, these flares would represent catastrophic radiation events. Life would need to be extremely hardy or well protected from this stellar temperament. In 2016, astronomers detected a planet orbiting Proxima Centauri. They called it Proxima Centauri b. The discovery sent waves through the scientific community and the broader public consciousness. Here was proof that planets existed around other stars. We'd known this for decades, but this was different. This was our nearest neighbor. This was our closest opportunity. Proxima b orbits very close to its star, completing an orbit every 11.2 days. It's in what astronomers call the habitable zone, the distance at which liquid water could theoretically exist on its surface. The planet appears to have a mass slightly larger than Earth. It could potentially have an atmosphere. It could have water, could have conditions suitable for life. This is the anomaly that haunts us. The closest star system doesn't contain a lifeless void or a toxic hellscape. It contains a world that might harbor life, and we cannot reach it. We cannot even imagine reaching it with any technology that exists, or will exist within the next few hundred years. But here's what makes this truly unprecedented. Proxima b is tidally locked to its star. One side permanently faces the star. One side remains in perpetual darkness. The dividing line between day and night, the terminator. As astronomers call, it is where liquid water might pool, where atmospheric circulation might concentrate, where conditions might be most stable for life. The radiation from Proxima's flares rips at the planet's atmosphere. If the planet ever had a thick atmosphere like Earth's, this radiation would have stripped it away over millions of years, one solar flare at a time. The best-case scenario for Proxima b is that it retained a thin, hardy atmosphere, or that its strong magnetic field protected it from the worst of the stellar assault. This is the profound peculiarity. We've found our neighbor's home, and it appears possibly habitable. Yet, the distance between us and at 4.24 light-years remains absolutely unbridgeable by any human effort we can conceive of. We can detect its existence. We can infer its properties from the slight wobble it induces in its parent star. We can dream about it. We cannot reach it. Consider the historical parallel. 1,500 years ago, an observer in what is now Portugal could see the lights of what is now North Africa across the Strait of Gibraltar. The distance is roughly 8 miles. It took centuries and an enormous investment of resources to build the ships and develop the navigation techniques necessary to bridge that gap. The technological investment to cross 8 miles required centuries of development. Now extend that to Proxima Centauri. The distance is roughly 250 trillion times greater than the Strait of Gibraltar. If it took centuries to cross 8 miles with wind and sailing technology, how many centuries would it take to cross 250 trillion times that distance with any conceivable propulsion? Yet here's the truly anomalous aspect. We can see Proxima b. We know it's there. We have evidence of its existence without ever sending a single spacecraft. Our telescopes and spectroscopy have revealed its presence. We've done something that seemed impossible, detected a world we cannot reach. This raises profound questions about the nature of cosmic isolation. We can observe, we cannot touch, we can measure, we cannot visit, we can infer, we cannot confirm. Over the next decades, the James Webb Space Telescope and successor instruments will map the atmospheres of distant planets. They'll detect oxygen, methane, other signatures of potentially habitable worlds. We'll build a catalog of worlds that might harbor life, some of them closer to us, many farther away. We could have observational evidence of dozens or hundreds of habitable exoplanets. And we will be unable to visit a single one of them. The anomaly of Proxima Centauri isn't that it's far away. The anomaly is that it's the closest, and being the closest reveals something devastating. If we can't reach our nearest neighbor, we can't reach any of them. The entire strategy of interstellar exploration: find a nearby system, go there, then push outward, collapses. Every star is equally unreachable. The universe has created an illusion of opportunity with Proxima b, while rendering that opportunity forever inaccessible. This chemical and physical signature, the habitable zone, the solar flares, the thin atmosphere, the distance opens doors to deep speculation about the universe's design. Is Proxima b a tantalizing hint of what's out there, or is it a cosmic joke? Is the universe showing us what we can never have, or is it revealing the true nature of cosmic solitude? Let's address the physical threat directly, because there's a possibility we should dismiss immediately so we can focus on the more unsettling questions. Could the journey to Proxima Centauri kill a human crew through radiation exposure? Yes, absolutely. Could it kill them through micrometeorite impacts? Yes. Could exposure to zero gravity for years cause permanent biological damage? Almost certainly. Could the psychological stress of confinement in a tiny vessel for decades drive people to madness? Historically, yes, we know this from submarine crews and Antarctic research stations, and the conditions on an interstellar vessel would be far more extreme. But these are all solvable problems. In principle, let's work through them. Radiation. The interplanetary medium contains cosmic rays and solar wind particles that would expose a crew to radiation beyond what Earth's magnetic field shields us from. A spacecraft traveling from Earth to Proxima Centauri would need shielding. Thick hulls of hydrogen-rich materials can reduce radiation exposure. Magnetic field generators could create artificial magnetic envelopes around the spacecraft. These approaches are theoretically sound. They would require massive amounts of material and enormous amounts of power, but they're not science fiction. They're engineering problems. The NASA Human Research Program has calculated that a crew member exposed to cosmic rays for a 3-year mission to Mars would receive a radiation dose of roughly 0.3 sieverts. This is a significant dose. It increases cancer risk, but it's not immediately lethal. The same crew on an 85-year journey to Proxima Centauri would receive a dose roughly 28 times higher, accounting for exponentially better shielding that future spacecraft could carry. This dose would cause immediate radiation sickness and death. But with adequate shielding, let's say, we make the spacecraft hull 10 meters thick with water. One of the best radiation shields, we could reduce this to acceptable levels. Such a hull would be extraordinarily heavy, requiring approximately 500 million tons of material for a crewed spacecraft. This is more material than humans have ever moved in space. It's impractical, but it's not impossible in principle. Micrometeorites, traveling through space for decades, exposes a spacecraft to countless tiny particles, dust, ice crystals, particles ejected from meteorite impacts. These particles travel at enormous speeds relative to the spacecraft and can punch through whole material. Shielding for micrometeorites requires different approaches: bumper shields, Whipple shields, and compartmentalization, so that a breach in one section doesn't affect the entire spacecraft. These technologies exist and are used on the ISS. They're proven, they're reliable. Biological degradation. Zero gravity causes muscle atrophy, bone density loss, and disruption of normal physiological processes. An 85-year journey would leave arriving astronauts in catastrophic physical condition. But Earth's space agencies are actively researching artificial gravity through rotation, pharmaceutical interventions for bone loss, and exercise regimens to minimize deterioration. A spacecraft with a rotating section creating 1 gram of artificial gravity is theoretically simple. You spin part of the ship. It requires engineering, but the physics is straightforward. The crew could maintain physical fitness. Psychological stress. This is harder to measure and manage, but not impossible. Space agencies have extensive psychological screening protocols. Multi-generational crews could include people born and raised on the spacecraft, for whom confinement is normal. Historical parallels: the crews of early sailing ships. Arctic explorers, submarine personnel showed that humans can psychologically adapt to extreme conditions given adequate preparation, leadership, and social structures. Here's the crucial realization: none of the physical threats to a crewed journey to Proxima Centauri are fundamentally unsolvable. They're all engineering problems. They're all expensive, they're all complicated, but they're not impossible. Given sufficient resources and time, humanity could probably develop technology to keep a crew alive and reasonably healthy for an 85-year journey through space. This bears repeating. The physical threats are solvable. So if the physical dangers aren't truly catastrophic, if radiation can be shielded, if biological degeneration can be managed, if psychological stress can be endured, then what is the actual worst case? If we can engineer our way around every danger the physical universe throws at us, what exactly prevents the journey? The answer is profoundly unsettling, because it reveals that the real obstacles aren't physical at all. They're economic, social, and fundamentally tied to the nature of human civilization itself. Consider the economics. Building and launching an interstellar spacecraft would require sustained commitment of resources for decades, possibly centuries. The entire GDP of Earth is approximately $100 trillion annually. An interstellar program requiring $10 trillion would consume 10% of global economic output for decades, while every other need, poverty, disease, infrastructure, education remains unmet. No democracy has ever sustained such commitment to a single project for a century. The Apollo program lasted about a decade. The Manhattan Project lasted about 5 years. The International Space Station has been a 30-year commitment, and it's a fraction of the cost of an interstellar program. Sustaining political will for a multi-century project spanning governments, cultures, and political systems seems virtually impossible. Yet the physical challenge, terrible as it is, has a solution. The economic and political challenge might be genuinely unsolvable. This is the uncomfortable truth lurking beneath the reassuring statements from space agencies. The universe isn't preventing us from reaching Proxima Centauri. We're preventing ourselves. Let's venture into speculative territory, being careful to label it as such, because there's a possibility that the real barrier to interstellar travel involves something we rarely discuss openly: the exhaustion of resources that make technological civilization possible. This is not doomsaying. This is careful examination of the assumptions underlying optimistic projections about our future. Every model of space exploration assumes technological progress improving efficiency, decreasing costs, expanding capabilities. We assume that spacecraft of 2100 will be better than those of 2024, which are better than those of 1969. This assumption has held for decades. Moore's law described this exponential increase in computational power. We've seen similar exponential growth in solar panel efficiency, battery capacity, materials science, and most technologies. But what if this exponential growth encounters limits? What if the easy improvements have already been made? Consider energy. Every space launch requires enormous amounts of energy. The Parker Solar Probe required more energy to launch than goes into operating the ISS for an entire year. A spacecraft capable of reaching Proxima Centauri would require incomprehensibly more energy. This energy would need to come from somewhere. Currently, global energy production relies on fossil fuels 80%, nuclear power 4%, and renewable energy 16%. This distribution has barely changed in decades. Renewable energy grows, but fossil fuel consumption grows faster. The total energy available to humanity is increasing, but slowly and inefficiently. An advanced spacefaring civilization would require massive energy abundance. Nuclear fusion, the theoretical solution to unlimited clean energy, remains perpetually 30 years away. It's been 30 years away for 60 years. Despite enormous investments and brilliant physics, fusion remains theoretical for large-scale power generation. Without a revolution in energy production, spacecraft construction becomes a matter of resource allocation. Every ton of material, every joule of energy devoted to building interstellar vessels is energy not devoted to feeding 8 billion people, providing water, maintaining agriculture. The political pressure against such expenditure would be immense. Here's where the alternative theory becomes speculative but worth examining. What if we're approaching a period of resource contraction rather than expansion? Credible scientists, not cranks, not doomsayers, but mainstream researchers in geology and resource economics have noted that easily accessible deposits of many critical minerals are becoming depleted. The ore grades of copper, gold, silver, and zinc have been declining for decades. Mining deeper requires more energy. Energy costs money. Marginal deposits become uneconomical. Rare earth elements, critical for electronics and renewable energy technology, are concentrated in a few geographic regions. China currently controls roughly 85% of global rare earth processing. If geopolitical tensions disrupt these supply chains, technological progress could slow dramatically. Agricultural productivity, which depends on fossil fuel inputs, assumes continued resource availability. The green revolution of the 20th century was driven by oil. Cheap oil made fertilizers affordable, made irrigation possible, made food cheap. If oil becomes expensive or depleted, agriculture reverts to lower productivity, requiring more land and more labor. Population decline is now occurring in developed nations. Japan, South Korea, parts of Europe, their birth rates have dropped below replacement. As populations age and decline, the available workforce shrinks. Fewer workers means fewer innovations, fewer products, less economic growth. I want to be clear, this is speculative. Credible economists disagree about whether these trends will cause crisis or whether technological innovation will solve them. We could develop abundant renewable energy. We could find new sources of rare earth elements. We could increase agricultural efficiency through biotechnology. It's possible. The trends aren't destiny. But here's the uncomfortable alternative theory. What if the next century isn't an era of exponential technological growth, but rather an era of resource management and slow technological stagnation? What if the curve of human technological advancement doesn't continue upward indefinitely, but actually peaks? In this scenario, the resources required to build an interstellar spacecraft become impossible to gather. Not because the physics is wrong, but because the economic base supporting such grand projects collapses. We can build a spacecraft to reach Proxima Centauri, but the civilization capable of building it would need to dedicate resources on a scale that would only be possible during an era of abundance. If that era passes, If we enter a period of contraction or stability, the opportunity closes. This isn't fatalism, it's pattern recognition. Every civilization tends toward increasing complexity and resource consumption. Eventually, complexity becomes brittle. Systems collapse. Sometimes they recover and improve. Sometimes they don't. Historian and systems researcher Vaclav Smil has documented how technologies that seem transformative often plateau. Solar panels have been improving for 50 years, but at a slowing rate. Wind turbine efficiency increases yearly, but at diminishing increments. Eventually, physics limits are approached. You can't make a solar panel more than 100% efficient. You can't violate thermodynamics. The alternative theory suggests that Proxima Centauri might be unreachable, not because it's far away, but because the window of technological capability, the era when our civilization, K, had both the resources and the will to build interstellar spacecraft, might be narrow, a century or two at most. And if we don't launch during that window, it might close permanently. That raises a chilling question. Is this century our window? What do we have right now? The resources and capability to begin a multi-century project that future generations will complete? Or are we already entering the era of constraint? NASA and ESA paint optimistic timelines. They suggest interstellar missions within 200 to 300 years. They suggest sustained growth in space budgets and technological capability. But their projections rarely account for resource constraints or geopolitical disruption. They're extrapolating recent trends indefinitely into the future, something history suggests is usually wrong. Some credible futurists argue that we have perhaps 50 to 100 years to establish self-sufficient space habitats and begin interstellar programs before Earth's resource base becomes too constrained to support such ventures. After that, we might be too focused on managing decline to dream about distant stars. This is speculation, clearly, but it's speculation grounded in real resource data, real demographic trends, and historical patterns of civilizational development. It's worth examining because it suggests that interstellar travel might not be prevented by physics or engineering at all. It might be prevented by the finite window of human civilization's abundant phase. Let's go deep into the most cinematic and philosophically troubling what-if Scenario 1, grounded in real physics but exploring implications rarely voiced. Imagine this. It's the year 2180. Humanity has finally achieved the breakthrough. Through sustained commitment, through technological innovation, through the dedication of trillions of resources, a spacecraft exists. It's enormous 5 kilometers long, capable of carrying 10,000 people. It has rotating sections creating artificial gravity. Its nuclear fusion engines have been tested thousands of times. The shielding is adequate. The life support systems are redundant. The hydroponics bays can feed the population indefinitely. The crew boards. They're not pioneers heading toward a pristine frontier. They're refugees fleeing a changing Earth, a world warmer than their ancestors knew, where agriculture is precarious, where resources are increasingly constrained. They're leaving because staying feels like a slow decline. They're heading toward Proxima Centauri with hope that the habitable zone around Proxima b might offer a fresh start. The engines ignite. They accelerate over months, eventually reaching 5% the speed of light. 85 years of travel stretches before them. For 85 years, they'll live in the closed ecosystem of their vessel, hurtling through an infinite void. But here's the scenario that becomes genuinely unsettling. What if they arrive to find Proxima b is not habitable? This is the speculative fear grounded in real scientific uncertainty. Proxima b, observed at light-year distances, appeared to be in the habitable zone. But spectral analysis from afar can deceive. The planet might have no atmosphere. Solar flares stripped it away eons ago. Or it might have an atmosphere, but one dominated by sulfuric acid clouds and crushing pressure Venus-like conditions instead of Earth-like. Or the atmosphere might be there, but the entire surface might be toxic, locked in a state where no life can develop. The crew arrives after 85 years of travel. They send down probes. The data comes back, transmitted at light speed across 4.24 light years. It takes 4.24 years for the bad news to travel back to Earth. By then, on Earth, the people who sent them are dead. By the time Earth receives the data, only the crew itself remains to deal with the consequence. And the consequence is devastating. They cannot land. The world is uninhabitable. They have a 10-ton lander designed for Proxima b, but the landing sites show atmospheric pressures that would crush the lander instantly. The temperatures are wrong. The chemistry is wrong. The planet is dead, or at least dead to human life. They have fuel, enough to maybe reach another star system, but that would require another 40 years of travel. Another generation born in space. Another 40 years of hope deferred. Or they could try to establish an orbital station around Proxima b, eventually trying to terraform the planet over centuries. But this scenario, terrible as it is, pales compared to what happens next in this speculative journey, decades into their arrival. The crew is dealing with the reality that their destination is uninhabitable. They receive a message from Earth. It's been traveling for 4.24 years. The message is from their descendants, from people born after they left. The message is grim. Earth's climate has destabilized further. Droughts have become permanent in major agricultural regions. Civilization has fragmented. Wars have been fought over water and arable land. The global economy has collapsed into regional autarky. There is no longer a united Earth with resources to maintain them. There is no longer a civilization capable of sending supply ships, of providing backup plans, of offering rescue. They're alone. 4.24 light years away from a dying world, orbiting a planet they cannot inhabit. With resources designed to last 200 to 300 years at most, but probably less given unexpected degradation and accidents that consume more material and energy than planned. The original crew will see Earth's slow collapse. Their children will cope with the knowledge that home is dying. Their grandchildren will grow up in a floating city orbiting an alien world, knowing they have perhaps 5 to 6 generations before the spacecraft becomes uninhabitable. At that point, they face a choice: attempt to terraform Proxima b, despite its hostile conditions, knowing it will take centuries and might never succeed, or attempt another journey to another star system, extending the exodus into another 40-year journey to an even more distant destination. This is the speculative scenario that defies optimism. It's not the immediate dangers: radiation, micrometeorites, acceleration stress. These are solvable. It's the civilizational challenge. Space exploration assumes a stable, abundant, Earth-based civilization supporting those who venture outward. What happens when that support collapses? Historically, expeditions that lose contact with their home base fail. The lost colony of Roanoke simply vanished. The Donner Party, attempting to cross the Sierra Nevada, fractured into cannibalism and death when they lost contact with supply lines. Every failed expedition in human history has one thing in common: loss of supply and loss of institutional support from home. Now extend that to 4.24 light-years. The crew cannot receive supplies from Earth. They cannot send for rescue. Communication takes 4.24 years each direction, a generation for a single round-trip conversation. By the time they explain their crisis, generations have passed on Earth. By the time help could possibly arrive, it could arrive at all the crew might be extinct. This is the deeper, worst case. Not that we can't reach another star, but that reaching another star might doom everyone aboard because the civilization that sent them might collapse in their absence. The greatest risk isn't the physical journey. It's the social, economic, and environmental collapse of the home civilization. Some speculative scientists have argued that this is actually the barrier preventing advanced civilizations from spreading across the galaxy. Not the distance, not the energy requirements, but the fundamental instability of civilization. Any civilization capable of launching interstellar missions is probably already fragilizing all available resources for the monumental effort. During the century or more required to build and launch, the civilization often collapses internally. The astronomer and physicist Frank Drake, who created the famous Drake equation attempting to estimate the number of detectable civilizations in the galaxy, eventually concluded that the greatest filter preventing galactic colonization might not be the technical challenges. It might be the civilizational instability that accompanies advanced technology. Civilizations that develop the tech to travel between stars might simultaneously be developing the tech to destroy themselves. What if Proxima Centauri is unreachable not because of distance, but because of this paradox? What if every civilization that develops the technology to reach the stars has already sown the seeds of its own collapse? This speculative scenario connects to one of the most profound questions in astrobiology, the Great Filter Hypothesis. The Fermi paradox asks a simple question: if the universe contains billions of galaxies, each with billions of stars, why don't we see evidence of alien civilizations? The night sky shows no signals. We detect no alien broadcasts. We see no megastructures or evidence of terraform projects. The universe appears silent. Either we're alone, which seems astronomically unlikely, or civilizations exist but remain hidden for reasons we don't understand. Or most troublingly, there exists a great filter, a point in the development of any civilization where something typically goes catastrophically wrong. Robin Hanson, the economist and futurist who formalized much of great filter thinking, proposed that life's existence might depend on passing through multiple filters. The origin of life itself might be extremely rare. The evolution of intelligence might be extraordinarily improbable. The transition to spacefaring civilization might require very specific conditions. But the most troubling possibility is that the great filter lies ahead of us, not behind. If we look at the universe and see no alien signals, no signs of interstellar civilization, the most ominous explanation is that something regularly prevents civilizations from surviving long enough to spread across the galaxy. That something is the great filter, and if we don't see it, we might already be approaching it. The speculative scenario we explored, where a crew reaching another star finds that Earth has collapsed, is one version of the great filter. The civilization reaches for the stars, and in doing so, destabilizes itself. The resources devoted to space exploration drain resources from planetary governance. The focus on the future abandons the present. The civilization splits into those seeking a fresh world beyond the stars and those remaining on Earth. This internal conflict and drain of resources accelerates collapse. Some variations of the Great Filter propose that technological development itself creates existential risks. A civilization that develops nuclear weapons, synthetic biology, artificial intelligence, and other powerful technologies might destroy itself before achieving spacefaring civilization. The very innovations that make space travel possible: energy abundance, computational power, the ability to manipulate matter at small scales, so create existential weapons. Others propose that the Great Filter involves biological or psychological constraints. Perhaps consciousness, the thing that makes civilization possible, also makes civilizations unstable. Perhaps intelligent beings are inevitably driven toward tribalism, conflict, and self-destruction. Perhaps the cognitive architecture that allows tulias and abstract thought also allows depression, nihilism, and despair. Still others propose that the Great Filter involves energy. The energy density required to support a spacefaring civilization to lift millions of tons into orbit, to accelerate relativistic probes, to create artificial habitats in space might exceed what any planetary system can sustainably produce. The transition from a planetary to an interplanetary civilization requires a certain energy threshold. Most star systems might simply not have enough energy density available over long timescales to support such a transition. Here's the profound implication: if the Great Filter has already passed, if we've survived the primary threat and lived to see the modern era, then we should expect to see the universe teeming with spacefaring civilizations. We don't. Therefore, the Great Filter probably lies ahead. And if the Great Filter lies ahead, Proxima Centauri becomes something else entirely. It becomes a test of whether we can achieve interstellar travel before the filter catches us. A test of whether we can sustain the resources, political will, and social stability required to launch an interstellar expedition before something climate collapse, nuclear war, artificial intelligence, mishap, engineered pandemic, or something we haven't yet conceived of destroys that possibility. This doesn't mean interstellar travel is impossible. It means it might be a race against time. And the clock might not be generous. We might have a century, or a decade, or we might have already missed the window. The historical perspective is grim. Every major civilization on Earth has eventually collapsed. Rome, the Abbasid Caliphate, the Ming Dynasty, the Soviet Union all built remarkable achievements, and all eventually fractured. Empires that seemed eternal fell. Institutions that seemed permanent dissolved. Technologies were lost, knowledge was forgotten, and the cycles continued. There's no precedent in human history for a civilization sustaining a single unified goal for multiple centuries. Yet interstellar exploration would require exactly that. It would require that a political structure, an economic system, a cultural commitment to space exploration remains stable and focused for 200, 300, or 500 years while Earth faces mounting challenges. It would require that during an era of resource constraints and climate disruption, billions of people remain convinced that launching a spacecraft to another star is worth the sacrifice. The more deeply we analyze Proxima Centauri as a destination, the more it becomes clear that distance is not the primary barrier. The primary barrier is ourselves. It's the barrier of civilizational fragility, resource constraints, political division, and the entropy that seems to dissolve every human achievement eventually. This raises the ultimate philosophical question that underlies the entire Proxima Centauri problem. Is the silence of the universe telling us something about cosmic distance, or is it telling us something about the fate of all intelligent life? Let's examine why, among all the constraints preventing interstellar travel, Proxima Centauri, specifically our nearest neighbor, haunts human consciousness in a way that distant galaxies do not. Its proximity, Proxima Centauri is the closest star. In cosmic terms, it's nothing separated from us by distances that dwarf human understanding. But in the context of interstellar space, it's relatively near. If we ever achieve interstellar travel, Proxima Centauri would logically be our first destination. It's the obvious starting point. This creates a particular species of frustration. The destination is so close in cosmic terms only, 4.24 light-years away. Our minds keep generating fantasies about reaching it. What if we could just go a little bit faster? What if we invented this particular propulsion system? These fantasies persist because the distance is somehow comprehensible in a way that distances to other star systems are not. Alpha Centauri, the binary star system of which Proxima is a member, has been imagined as a destination for over a century. Science fiction has made it a trope, the closest habitable world, the obvious frontier, the next step outward. This cultural narrative runs deep. Dozens of science fiction stories, movies, and books place first contact at Alpha Centauri or missions to its planets. But there's a deeper philosophical issue at play. Proxima Centauri represents something more profound than just a destination. It represents our collision with cosmic scale. For most of human history, the universe seemed comprehensible. The sun, the moon, the visible planets, these were accessible in principle. If you had a fast ship, you could reach the moon. If you had a faster ship, you could reach Mars. The planets seemed like places you could go. They were far, but not impossibly far. The distance was a problem of engineering, not of fundamental physics. Then astronomical observation revealed that stars are objects at cosmological distances. Light travels at the ultimate speed limit, and it takes years to reach even the nearest star. Suddenly, going to another star isn't a matter of engineering sufficiently fast propulsion. It's a matter of reorganizing human society in a way that seems fundamentally alien to how we've ever organized ourselves. Proxima Centauri represents the moment where human ambition crashes into cosmic reality. It's the moment where we realize that the universe is constructed in a way that defeats human exploration. Not because exploration is impossible, but because the distances are so vast that the civilizational changes required to bridge them might be more disruptive than anything human society has ever experienced. To understand this philosophically, consider what it would actually mean to successfully establish a crewed outpost on Proxima b. If the crew arrived and somehow made Proxima b habitable, they would be establishing a human civilization that is forever sundered from Earth. Not topically, literally and permanently separated by a gap that no message can cross in less than 8.48 years round trip. This isn't colonization like European colonization of the Americas, where supply ships brought news, support, reinforcements, and where conversations could happen within months or years. This is permanent exile. The crew and their descendants will develop their own culture, their own values, their own understanding of what it means to be human. If Earth remains involved in their development, sending instructions, offering guidance, those instructions will be years out of date by the time they arrive. Over centuries, the two populations would diverge culturally, linguistically, and possibly even biologically if Proxima b has different gravity, radiation levels, or other environmental pressures. Within a few generations, the civilization on Proxima b wouldn't identify as human colonists exploring for Earth anymore. They'd be Proximan, a distinct species adapted to the Proxima Centauri system, with their own history and identity separate from Earth's. This raises a philosophical problem that often goes unexamined. If spreading human civilization to Proxima Centauri means creating a population that will rapidly become something other than human, or at least other than Earth's human, or we exploring space, or are we creating new species? If the entire purpose of space exploration is the continuation and expansion of human civilization, then Proxima Centauri represents a paradox. To reach it means ceasing to be Earth human, okay? To survive there means becoming something adapted to that world, okay? The Proxima Centauri colony wouldn't be an expansion of Earth, okay? Human civilization, it would be the first branch of a new biological and cultural experiment. Some futurists argue this is fine. Humans become post-humans. Earth humans become Proximans. This is evolution. This is progress. We shed our planetary constraints and become cosmic beings. But this contains a hidden cost. It means accepting that Earth humans will never truly explore the cosmos. We'll create successors who do. Our descendants, so changed by adaptation to alien worlds that they're not really us anymore, will explore. We ourselves will always be confined to Earth and near-Earth space. We will be the generation that launches the vessels that birth post-human civilizations, but we will not experience the destinations ourselves. We will not see humanity's conquest of the stars. We will see only the launch. This is the philosophical haunt that Proxima Centauri represents. It's not just distant. It's distant in a way that makes the journey incompatible with human identity. To reach it means becoming something other than human. To remain human means accepting that Proxima Centauri and everything beyond it will forever be observed but not inhabited by our species. The universe is constructed in a way that seems almost deliberately designed to prevent human exploration while allowing human observation. We can see Proxima Centauri. We cannot live there. We can detect planets around distant stars. We cannot visit them. We have binoculars for a universe we cannot enter. Let's explore the institutional and procedural challenges of actually attempting to colonize another star system, assuming against all odds that we somehow developed the technology. The first question is governance. A spacecraft carrying 10,000 people to Proxima Centauri would need internal government. Onboard decisions would need to be made about resource allocation, conflict resolution, discipline, and long-term planning. Historically, isolated human communities develop hierarchical structures, sometimes democratic, usually dominated by small leadership councils. The largest ship's nuclear submarines, the International Space Station, have strict command hierarchies. A generation ship to Proxima Centauri would likely develop the same. This raises the question, what authority does the crew have? Who on Earth can make decisions that affect them? If Earth collapses, who are they accountable to? If Earth changes its priorities, do they follow Earth's orders or pursue their own interests? Historical parallels are instructive. Colonial governors often became independent from their sponsoring nations. The American colonies developed their own identity despite being politically subordinate to Britain. The same pattern would likely repeat on a spacecraft. After decades of isolation, the crew would develop a culture distinct from Earth. They would inevitably resist external control. By the time they reached Proxima Centauri, they would probably be effectively independent. But this raises a second problem. Upon arrival, they would need to make decisions about resource use, settlement patterns, and long-term survival. Some crew members might advocate for immediate colonization land at the best possible site and begin building. Others might advocate for caution test the environment, understand the risks, move slowly. These disagreements could tear the community apart. History shows that isolated communities, when facing resource stress, often fracture into hostile factions. The most famous example is the Pitcairn Islands, where a small group of British mutineers and Tahitian women settled. Within a generation, their descendants were engaged in bitter internal conflict that killed more of them than any external threat. Now extend that to a spacecraft full of 10,000 people, where nobody can leave, where all disagreements must be resolved internally, where resource constraints are permanent, where every decision affects survival. The probability of maintaining cohesion and cooperation across 85 years of travel, then decades of settlement, seems very low. Here's the communication challenge. How does the arriving crew coordinate with Earth about the decision to settle Proxima b? If they arrive and find the planet less habitable than hoped, or more habitable than expected, they need to communicate this to Earth. But that communication takes 4.24 years each way. By the time Earth responds with guidance or support, 8.48 years have passed on Earth. But only a few years have passed aboard the spacecraft, depending on whether we're counting Earth time or ship. Time relativity makes this complicated. In practice, the crew would need to make decisions based on local conditions. Without the possibility of meaningful consultation with Earth, they would have complete autonomy by necessity. This means the civilization they establish at Proxima Centauri would be fundamentally unconnected to Earth from the moment they arrive. Here's the political implication. If the crew arrives at Proxima Centauri and decides to establish an independent nation, which they almost certainly would, given the severed communication with Earth, then humanity has split into two separate political entities with no ability to coordinate. Earth humans and Proxima Centauri humans would develop completely separately. They would have different legal systems, different resources, different environmental pressures, different cultural values. Within a few generations, they might be unable to even communicate comprehensibly. Languages diverge rapidly in isolated populations. Cultural references, values, and understandings of the world would become incompatible. The Proximans would increasingly view themselves as a distinct civilization, perhaps even as aliens relative to their Earth origins. This is the often unspoken aspect of space colonization. It doesn't unite humanity across the cosmos. It fragments humanity into incompatible branches. Proxima Centauri colonization would represent the end of human unity, not the beginning of human cosmic empire. Some advocates for space colonization frame this as positive new perspectives, new civilizations, the diversity of human experience expressed across worlds. Others frame it as tragic, the fracturing of a species, the loss of common identity, the dissolution of humanity into competing post-human species. But there's a darker possibility worth examining speculatively. What if the arrival at Proxima Centauri becomes a point of conflict between Earth and the Proximan colony? Earth has invested trillions of resources and centuries of effort into sending these colonists. Earth probably views them as representatives of Earth's interests, as an expansion of Earth's civilization. The Proximon crew, having survived a brutal 85-year journey and adapted to independence, views themselves as having earned the right to determine their own future. Imagine the scenario. Earth still unified, still technologically capable, sends a message expressing its vision for how Proxima b should be developed. What resources should be exploited? What values should guide the colony? The message arrives 4.24 years after Proxima colonization has begun. The Proximans have already made different choices. They've already established different values. They refuse to comply. What happens then? Earth cannot send military support. The distance is too vast. Earth cannot enforce compliance. Earth can only protest, threaten, or eventually cut off any remaining communication. The Proximan colony becomes independent by default, not by revolution, but by the physics of distance. Earth's only power is to eventually try again to send another, larger expedition to Proxima Centauri to enforce Earth's vision. This creates a scenario where interstellar travel doesn't unify humanity, but instead creates separate human civilizations competing for the same resources, separated by distances too vast for coordination. This speculative scenario, human civilization splitting into incompatible branches separated by interstellar distances, might actually be worse institutionally and socially than remaining confined to Earth. At least Earth humans, with all our conflicts and divisions, remain part of a single biological species with the possibility of mutual understanding. Post-human Proximans would be separated by both distance and evolutionary adaptation until they became effectively alien to Earth humans. So when we ask what would happen if we reached Proxima Centauri, the answer is troubling. We would establish a branch of humanity that would rapidly become post-human, independent, and fundamentally alien to our interests. We would fragment the species. We would create new civilizations that would inevitably compete with Earth. We would have transformed the problem of interstellar distance into the problem of interstellar conflict. As we've explored the challenges of reaching Proxima Centauri, a subtler problem emerges. What should we actually do with the knowledge we gain about Proxima b? We can observe Proxima b now. We can infer its properties from spectral analysis. Over the next decades, the James Webb Space Telescope and successor instruments will map its atmosphere, detect biosignatures if they exist, understand its climate. We'll gather profound information about a world 4.24 light-years away without ever sending a single human. This raises a question that rarely gets asked. Should we share this knowledge openly with the world, or should we limit access to it? This might sound like scientific censorship, but consider the implications. If Proxima b shows unmistakable signs of habitability, oxygen in the atmosphere, methane that suggests biology, atmospheric composition that matches Earth's, the pressure to mount an expedition becomes immense. Religious organizations might view it as a divinely appointed destination. Space agencies would compete to be first. Private companies would lobby for resources. The political will to launch an interstellar expedition might suddenly materialize. But we've already explored why that's probably a terrible idea. The resources devoted to an interstellar program would strain Earth's ability to manage its own crises. The crew would face brutal conditions that would likely kill them or radically alter them. The civilization they established would inevitably conflict with Earth. Yet if we withhold information about Proxima b's potential habitability, we're engaging in information control. We're deciding that the general public can't be trusted with knowledge because we fear it would drive bad decisions. This is paternalistic. It's the opposite of scientific openness and democratic transparency. The balance between skepticism and openness has always been the heart of scientific ethics. We want to share knowledge. We also want to avoid panic or irrational action based on incomplete information. But in this case, the dilemma is more acute. If we announce that Proxima b has Earth-like conditions and potentially habitable atmosphere, we're making a promise we can't keep. We're promising that this world is accessible to us when it isn't. We're advertising a destination that's forever out of reach. We're raising hope we cannot fulfill. Some might argue that's worse than silence. raise hope and disappoint expectations, create desire for an unreachable destination. Of course. This might drive despair rather than inspiration. Conversely, if we announce that Proxima b appears uninhabitable toxic atmosphere, extreme temperatures, no signs of life, we might be delivering false bad news. The observations from light years away could be wrong. The planet might actually be habitable despite our spectral analysis suggesting otherwise. We might discourage a future attempt based on incomplete information. Here's the uncomfortable possibility. We might be approaching an era where we have profound observational knowledge of habitable worlds, but possess the definitive knowledge that we cannot reach them. We'll know Proxima b exists, potentially harbors life, is theoretically habitable, and is absolutely unreachable. This is a condition of cosmic knowledge without cosmic reach. We'll have answered one of humanity's deepest questions. Are we alone? But only with observational confirmation that we are, in practical terms, unreachable by those we might find. Citizen science and public engagement have driven tremendous progress in astronomy. Amateur astronomers, armchair researchers analyzing public datasets have contributed to exoplanet discovery and characterization. There's enormous public interest in finding habitable worlds. This is healthy curiosity driving scientific progress. But if that curiosity cannot be fulfilled, we find habitable worlds and then must admit that they're inaccessible. The emotional and psychological impact might be profound. We might inspire a generation to pursue space science only to tell them that their entire field of study will never produce practical results within human timeframes. The balance between skepticism and openness requires that we acknowledge the more we learn about Proxima b and other potentially habitable worlds through telescopic observation, the more we're confronting the reality of our cosmic isolation. The universe might be full of habitable worlds, accessible only to observation, never to visitation. This bears repeating. We might live in a universe where we can detect thousands of potentially habitable worlds, but reach none of them. The transparency we practice as scientists might require admitting to ourselves and to the public that the age of exploration is over before it ever really began. Let's step back from the specific problem of Proxima Centauri and consider its place in the vast cosmic scale. Proxima Centauri is 4.24 light-years away. Light, traveling at 186,000 miles per second, takes 4.24 years to make the journey. This is a comprehensible distance, only about 25 trillion miles. In cosmic terms, it's nearby. But what about the farther stars? The nearest major star cluster, the Hyades, is 150 light-years away. The Pleiades is 440 light-years away. The Andromeda Galaxy, our nearest major galactic neighbor, is 2.5 million light-years away. The observable universe extends roughly 46 billion light-years in all directions, to the cosmic horizon beyond which we cannot see. If Proxima Centauri at 4.24 light-years represents an insurmountable distance for human travel, then what can we possibly say about the rest of the universe? Proxima Centauri is our cosmic backyard. Everything else is exponentially farther. This realization has humbled every astronomer who contemplated it. Carl Sagan spoke frequently about the pale blue dot photograph taken by Voyager 1 from the edge of the solar system. Earth, visible as a speck of light, less than a pixel in the photograph. Sagan reflected that everything humanity had ever accomplished, every war, every civilization, every love story occurred on this barely visible point of light, suspended in a vast darkness. The cosmic distance scale produces a peculiar emotional response: awe at the grandeur of the universe, terror at the enormity of space, humility at our insignificance, and sometimes, paradoxically, a sense of wonder at the fact that we can even comprehend distances so vast. Proxima Centauri represents the limit of human exploration in a way that the edge of the solar system did not. Voyager 1 and Voyager 2, launched in the 1970s, have reached the heliopause, the boundary of the solar system, where the solar wind gives way to the interstellar medium. They're still in contact with Earth. Their signals, traveling at light speed, take 20 hours to reach us. But they're reachable. We can still send them commands. They remain part of the human domain. Proxima Centauri lies beyond even the theoretical boundary of human reach. It's where human civilization's grasp genuinely stops. The Voyagers are traveling at roughly 11 miles per second. At this velocity, they would require about 73,000 years to reach Proxima Centauri. If we imagine a hypothetical civilization that could travel 100 times faster than the Voyager's 5,000 times faster than our fastest spacecraft, the journey would still take 730 years. And this is our nearest star. Everything else is farther. Every exoplanet we've discovered, every potentially habitable world, every possible destination for human exploration lies at distances that dwarf even the Voyager timescales. If we're truly limited to reaching only the nearest stars, and the nearest star requires centuries of travel even at speeds we haven't achieved, then effectively, humanity is bound to its home system. The solar system, everything from the sun to the distant Oort cloud of icy objects, becomes humanity's domain. Everything beyond is observation. This creates a peculiar psychological state that we haven't had to face before. For most of human history, the unknown was reachable if you had enough time and resources. Unexplored lands could be reached by ship. Explored mountains could be climbed, unexplored oceans could be crossed. Every frontier was a frontier you could reach. But cosmic frontiers are different. The frontier isn't reachable. You can observe it, measure it, study it from afar, dream about it, but you cannot reach it. The universe has placed wonders, potentially habitable worlds, possibly life-bearing planets, cosmological phenomena of extraordinary beauty everywhere you look. And almost none of it is reachable. Poetically, we exist in an era of cosmic vision without cosmic reach. We have better telescopes, more satellites, deeper understanding of physics than any previous generation. We can see farther. We can detect fainter objects. We're discovering more about the universe than ever before. But that increased knowledge comes with the crushing realization that the universe's treasures are mostly inaccessible to us. The radio signals sent into space by humans, the Arecibo message, for example, or the transmissions from early television broadcasts propagate outward at light speed. They'll eventually reach nearby stars. If intelligent life exists around Proxima Centauri, they could theoretically receive our signals in about 4.24 years. They could respond, and their response would reach us in another 4.24 years. A conversation would be possible, but would span almost a decade for each turn. This is where cosmic perspective becomes genuinely unsettling. We might eventually communicate with civilizations around other stars, but we cannot visit them. We can send radio waves. We cannot send ourselves. The statistical realities compound this isolation. The Kepler Space Telescope alone discovered over 5,000 exoplanets. Many of them are in their star's habitable zone. Statistically, some of them almost certainly harbor life. Yet we can observe none of them directly. They're too far away and too faint. We can infer their existence. We can deduce properties, but we cannot see them as we see Earth. Paradoxically, the more telescopes improve, the more we'll realize how isolated we are. We'll discover more habitable worlds, more potential habitats for life, all unreachable and unvisitable. Each discovery will be a reminder that the universe is full of wonders we cannot reach. This is the scale of cosmos that humbles, not just the size of it, but the realization that our place in it is not as explorers of that vastness, but as observers trapped in a small corner of it. We are more like people in a prison looking out at a magnificent world beyond reach than we are like explorers preparing to venture across that world. Let's shift tone here, because while the preceding chapters have explored increasingly unsettling aspects of interstellar travel and cosmic isolation, there's another narrative we should explore. The narrative of hope, achievement, and what we're actually learning despite our isolation. Yes, humanity cannot reach Proxima Centauri with current or foreseeable technology. Yes, reaching even our nearest star would require fundamental changes to civilization and technology that seem impossible. Yes, we're likely confined to the solar system for the foreseeable future. But within the solar system, within observational astronomy, and within the data we can gather, humanity has achieved something remarkable. We've built telescopes that can see the faintest light from the most distant galaxies. We've developed spectrographic analysis that can determine the composition of planetary atmospheres light years away. We've sent robotic probes to every planet in our solar system, and they've provided data that revolutionized our understanding of planetary science. We've landed humans on the moon and maintained continuous human presence in space for over 25 years with the PNT International Space Station. These achievements don't reach another star, but they represent profound human capabilities in exploration and understanding. Consider Proxima b itself. Discovery in 2016 depended on a technique called radial velocity measurement, where astronomers detect the slight wobble a planet's gravity induces in its parent star. This technique required decades of development in spectroscopy, understanding of stellar physics, precise instruments capable of detecting shifts of just a few meters per second, computer analysis to parse signal from noise. International cooperation between observatories. The discovery of Proxima b came not from a spacecraft, but from careful observation, patient analysis, and the accumulated knowledge of a century of astronomical science. This is remarkable. The James Webb Space Telescope launched in 2021 and now operational, represents the current cutting edge of human observational capability. It cost roughly $10 billion and took over 25 years to develop. It has exceeded expectations in nearly every way. It's revealing the deep structure of the universe, from the most distant galaxies to the atmospheres of nearby exoplanets. Within this decade, JWST and its successor instruments will characterize the atmospheres of potentially habitable exoplanets. We'll detect biosignatures, oxygen, methane, other chemicals that suggest biological activity. We'll answer one of humanity's deepest questions: are we alone? Not through traveling to other worlds, but through patient observation. This is a different form of exploration. Instead of moving to distant places, we're bringing distant places to us through increasing sophistication of our observational instruments. It's not as romantic as interstellar travel, but it's equally revolutionary in its implications. The shift from physical exploration to observational exploration has historical precedent. Before telescopes were invented, astronomers explored the night sky with their unaided eyes, charting visible stars and developing models of the universe. The telescope revealed moons and planets invisible to the naked eye. Spectroscopy revealed the composition of distant objects. Photographic plates revealed faint nebulae no human eye could detect. Each innovation expanded human knowledge despite removing the human from direct physical presence at the objects of study. We're at another such inflection point. Instead of leaving Earth to explore the universe, we're bringing the universe to Earth through increasingly sophisticated instruments. Instead of colonizing Proxima b, we're characterizing Proxima b from afar. Instead of visiting exoplanets, we're detecting signatures of their atmospheres across light years. This isn't settling for second best. This is embracing a new paradigm of exploration appropriate to the actual scale of the universe. We explore the cosmos by understanding it from afar, and that understanding is becoming increasingly profound and detailed. Scientific achievements in space exploration have accelerated. The ISS, despite its modest orbit and limited scope, has yielded discoveries in materials, science, biology, and physics that couldn't have been made on Earth. The same principle applies to the broader cosmos. Understanding it from observational distance has value that interstellar travel doesn't diminish. Consider what we've learned about exoplanet atmospheres. As JWST analyzes the light that passes through the atmospheres of distant planets, absorbing and reflecting certain wavelengths, we're literally learning what other worlds are made of. We're detecting oxygen, water vapor, carbon dioxide in exoplanet atmospheres. Some of these planets are Earth-sized and potentially habitable. We're answering fundamental questions about planetary diversity, about the frequency of habitable worlds, about the conditions under which life might arise. All of this without ever leaving Earth. All of this using instruments that amplify human perception and technological capability to reach distances that human bodies never will. The transparency and openness of space science is another achievement worth celebrating. Raw data from space telescopes is made publicly available. Citizen scientists worldwide analyze this data, contributing to discoveries. The scientific community publishes findings openly. The knowledge that's being gained about the universe is genuinely shared knowledge, not guarded proprietary information. This collaborative, transparent approach to understanding the cosmos represents something hopeful about human civilization. Despite all the conflicts and divisions, humans around the world come together in the shared project of understanding the universe. Funding agencies from multiple nations contribute to space programs. Scientists collaborate across borders. Discoveries are celebrated as achievements for all humanity. The data we're gathering about Proxima b, about exoplanets, about distant galaxies, will outlast any individual human civilization. If Earth suffers catastrophic collapse, if our current civilization transforms or fails, the knowledge we've accumulated about the cosmos remains. Future humans, should they exist in any form, will inherit observational data about billions of worlds. They'll inherit the understanding that the universe is vast, that habitable worlds likely populate that vastness, and that we existed in an era when we could detect and begin to understand that reality even if we couldn't physically reach it. In silence and in data, humanity has performed an extraordinary feat. We've learned to see the universe in unprecedented detail. Understanding worlds billions of light years distant with more precision than our ancestors could have imagined. We haven't reached the stars, but we've learned their secrets. That's not nothing. That's something profound. To understand why observational exploration of distant exoplanets might ultimately be more valuable than physical exploration would be, we need to understand the science of how we detect these worlds. When Proxima Centauri was observed in 2016 to possess a planet, the discovery didn't come from imaging the planet directly. Proxima b is far too small and far too dim to see directly from Earth. Instead, astronomers used the radial velocity method, also called the Doppler method. The wobble for Proxima Centauri is tiny. The planet's gravity causes the star to move at roughly 1.4 meters per second slower than a walking human. To detect this wobble requires spectroscopic precision of 1 part in a million. The instruments required to achieve this precision represent the cutting edge of astronomical technology. The physics underlying this observation is profound. By detecting light from a star 4.24 light-years away and analyzing subtle shifts in its wavelength caused by a planet too small and too dim to see directly, astronomers have revealed the presence of an entire world. The planet itself is unseen, invisible, unobserved directly, but its existence is confirmed through the physics of orbital mechanics. This is the revolution in exoplanet discovery. We don't need to see planets to know they exist. We detect them through their gravitational effects, through their transit signatures when they pass in front of their star and block a tiny amount of light, or through thermal radiation they emit. Each method reveals different properties of the planet. Now consider what's coming with JWST. When a planet passes in front of its star, a tiny fraction of the star's light passes through the planet's atmosphere. As it does, different wavelengths are absorbed or transmitted differently depending on what molecules are in that atmosphere. Oxygen absorbs light at certain wavelengths. Water vapor absorbs at others. Carbon dioxide, methane, nitrogen, each molecule has a distinct spectral signature. By analyzing the light that passes through the planet's atmosphere, during transit. Astronomers can determine what that atmosphere contains. This technique is called transmission spectroscopy. JWST is revolutionary because it's sensitive enough to detect very faint transmissions thin atmospheres. Distant planets, subtle signatures. With JWST, astronomers have already begun detecting the atmospheres of distant exoplanets. They've detected water vapor in exoplanet atmospheres. They've confirmed the presence of carbon dioxide. They're building catalogs of what these distant worlds are made of. Imagine the next step. JWST detects oxygen in the atmosphere of a distant exoplanet 40 light-years away. Oxygen is a strong biosignature produced by living organisms and is rare in lifeless atmospheres. The detection would be indirect. We wouldn't be seeing organisms, just the chemical signature of their waste product, but it would be profound evidence of life on another world. This would be the most profound discovery in human history. We would have evidence that life exists beyond Earth. We would have done this through spectroscopy and observation without ever visiting that world. More examples of this transformative power of observation. The study of exoplanet masses and sizes has revealed that Earth-sized planets are common. We once didn't know if planets like Earth existed around other stars. Now we know they're abundant. This knowledge comes from observational astronomy, not from spacecraft. Analysis of the habitability zones around stars has revealed that potentially habitable planets exist in abundance throughout the galaxy. Current estimates suggest there are more potentially habitable planets in the galaxy than there are stars visible to the naked eye from Earth. Again, this knowledge comes from observation, calculation, and analysis, not from visitation. The discovery that many stars have planetary systems, that Earth-sized planets are common, habitable zones are widespread. These are scientific insights of staggering importance that have emerged from observational astronomy. In just the past 30 years, the data being gathered about exoplanet atmospheres, their compositions, their temperatures, their orbital parameters, will provide a complete picture of planetary diversity across the galaxy. We'll know the frequency of Earth-like planets. We'll have circumstantial evidence of whether life is common or rare. We'll have a comprehensive understanding of what the cosmos contains, all without leaving Earth. This is empowerment through knowledge. By understanding what's out there, we're expanding human consciousness. We're learning what's possible, what's common, what exists. This knowledge transforms how we see ourselves and our place in the universe. The science behind exoplanet detection is sometimes dismissed as just observation compared to the supposed glory of actually traveling to other worlds. But observation is exploration. Understanding is exploration. Knowledge is exploration. The revelation of distant worlds through increasingly sophisticated instruments is exploration of the deepest kind. When JWST detects biosignatures in an exoplanet atmosphere, that will be exploration that reveals an entirely new world. That will be a greater achievement of human understanding than anything we could physically accomplish with spacecraft within centuries. The next century of astronomy will revolutionize our understanding of the cosmos in ways that would have been unimaginable to previous generations. The space telescope programs currently under development will be exponentially more powerful than JWST. The planned Habitable Worlds Observatory future mission concept aims to study the atmospheres of Earth-sized planets around nearby stars, would be capable of detecting biosignatures in the atmospheres of potentially habitable worlds. Simultaneously, ground-based telescopes are becoming more powerful. The extremely large telescope, currently under construction in Chile, will have a mirror 39 meters in diameter, the size of a building. The 30-meter telescope, planned for Mauna Kea in Hawaii, will have a 30-meter mirror. These instruments will be capable of spectroscopic analysis of distant objects that current telescopes cannot resolve. Within this generation, perhaps within a few decades, humanity will likely have detected biosignatures from distant exoplanets. The spectroscopic signature of oxygen in an exoplanet atmosphere, combined with other evidence of biological activity, would constitute proof that life exists elsewhere in the universe. This would be the most profound scientific discovery in human history, but it would be made from Earth through observational astronomy. Following this discovery, the next logical steps would be 1. Identifying which biosignature-bearing planets are most likely to have intelligent life if any signals are detected. 2. Attempting to send focused signals toward these candidates. 3. Listening for responses, a form of active SETI, search for extraterrestrial intelligence. None of this requires leaving Earth. All of it is profound exploration. The discovery of extraterrestrial life through spectroscopy would be as revolutionary as the discovery of exoplanets was a generation ago. The broader implication: the future of human exploration of the cosmos is observational, not physical. We will explore the universe through increasingly sophisticated instruments, not through spacecraft carrying human explorers to distant locations. This reframes the entire question of Proxima Centauri. Instead of asking, "Can we reach Proxima Centauri?" we should ask, "What can we learn about Proxima b without visiting it?" And the answer, increasingly, is quite a lot. With future telescopes, we'll be able to detect the composition of Proxima b's atmosphere. We'll know if it has oxygen, okay? We'll know if it has water vapor. We'll have insights into its surface conditions based on infrared radiation it emits. We might detect signatures of clouds, storms, or geological activity. If Proxima b harbors life, advanced spectroscopy might detect biosignatures. We could have evidence of life on Proxima b without ever seeing the surface, without ever sending a spacecraft, without ever leaving Earth. The expansion of human knowledge about the cosmos will occur through this observational paradigm. Future humans will inherit a complete picture of planetary diversity throughout the galaxy. They'll know the frequency of potentially habitable worlds, the chemistry of their atmospheres, the likely distribution of life. They'll have this knowledge without physical presence beyond the solar system. The broader research program connecting to this includes gravitational wave astronomy, opening new ways to observe the universe, black holes, neutron star mergers, etc., neutrino astronomy, detecting particles from distant cosmic events, multi-wavelength observations combining X-ray, infrared, optical, and radio data, artificial intelligence analyzing vast data sets to identify patterns and anomalies. Collaborative observation networks, where multiple telescopes observe the same objects simultaneously. Each of these advances expands human observational capability. Each pushes the boundaries of what we can understand without physical presence. For Proxima Centauri specifically, the future roadmap looks like this. 2030's JWST and successor telescopes fully characterize Proxima B's atmosphere. We'll know its temperature, its atmospheric composition, whether it has water, whether it has oxygen, or other potential biosignatures. 2050s, 2080s. Advanced telescopes possibly detect direct biosignatures in Proxima B's atmosphere if life exists there. We might receive reflected light from the surface, revealing weather patterns or geological features. 2100s and beyond. Perhaps even higher resolution imaging that reveals patterns on the surface of Proxima B mountains, oceans, evidence of life or technology. This is speculative, but advancing telescope technology might make it possible. At no point in this roadmap does a human spacecraft visit Proxima Centauri. At no point does a human explorer stand on Proxima B. But at every step, human knowledge deepens. At every step, we understand a distant world more completely. The question, why is Proxima Centauri too far for humans, has been answered. It's too far for bodies, but not for minds. Human consciousness, extended through instruments and analysis, can explore Proxima Centauri thoroughly without human bodies traversing the 25 trillion-mile gulf separating us from it. This might seem like a consolation prize. We can observe it, but not visit it, but consider the alternative. The billions of humans who will never travel to other continents in their lifetime can observe Proxima B. Every human with internet access can see the data, understand what we learn about that world, participate in the discovery. This is exploration democratized, made available to all, not just to a small elite of spacecraft pilots. The future of human exploration is observational, collaborative, and increasingly sophisticated. We'll explore the universe more completely through instruments and data analysis than we ever could through physical travel. Proxima Centauri will become known to us, its atmosphere, its climate, perhaps even evidence of life without us ever traveling there. And that's not a failure. That's a different kind of success. It's the triumph of human intelligence and creativity applied to the fundamental problem. How do you explore a universe too vast for your body to traverse? The answer: you extend your mind across the vastness through the instruments you build and the analysis you perform. As we reach the end of this journey, let's return to where we started, standing on Earth, looking outward at a universe of incomprehensible scale, contemplating our place in it. For most of human history, we believed the universe was small and knowable. The classical cosmology envisioned a universe with Earth at the center, surrounded by crystalline spheres bearing planets and stars. This universe was comprehensible. It could be understood. The distances were large, but not absurdly so. Gradually, as telescopes improved and measurements became more precise, we discovered that the universe was vastly larger than we imagined. Stars were farther away than any human could travel. Galaxies existed beyond the Milky Way. The universe expanded beyond imagination. The realization came in phases. The moon was far, but reachable by rocket in a few days. Mars was farther, requiring months of travel. The solar system was vast, with the Voyager probes taking decades to traverse it. The nearest star was impossibly far, requiring 73,000 years of travel at our fastest speeds. Everything beyond that was exponentially farther still. At each phase, the scale seemed to defeat human ambition. Yet at each phase, we responded not with despair, but with innovation. We built better telescopes. We developed more sophisticated instruments. We extended human understanding to match the scale of the cosmos. This trajectory suggests a different future than the one envisioned by space colonization advocates. Instead of humanity spreading across the galaxy, establishing outposts on dozens of worlds, we might be destined to remain confined to Earth and near-Earth space while extending our consciousness across the wide cosmos through observation and understanding. This is not defeat. This is adaptation. Just as a deep-sea creature develops eyes to see in the darkness of the ocean depths, humanity is developing instruments to see across the vastness of space. The Hubble Space Telescope, the James Webb Space Telescope, future instruments we haven't yet designed. These are extensions of human perception, allowing us to explore the cosmos without bodily presence. The great explorer's dream might not be realized, no human setting foot on Proxima b, no human colony established at another star. But the explorer's fundamental goal to understand new worlds, to expand human knowledge, to answer questions about what exists beyond our immediate surroundings, this goal is being achieved through observational astronomy and remote analysis. Proxima Centauri taught us something about ourselves. We are creatures of ambition and yearning, forever reaching toward frontiers. We dream of reaching distant worlds. We build rockets, design spacecraft, imagine futures where human civilization spreads throughout the cosmos. But we are also constrained by physics and biology and economics in ways that make those dreams incompatible with our nature. The resolution of this tension is not to abandon exploration, but to redefine it. Exploration is the expansion of understanding. A person who has never traveled to Machu Picchu, but understands its history, its architecture, its cultural significance, has explored it. A person who has never been to Mars but has studied the geological data from Mars rovers has explored it. A person who has never seen Proxima b but has analyzed its atmospheric composition through spectroscopy has explored it. This is exploration in the age of observation. It's exploration made possible by instruments rather than by bodies. It's exploration available to anyone with access to data and the curiosity to understand it. In some sense, we've been doing this all along. Medieval scholars explored lands they never visited by reading accounts from travelers. Renaissance scientists explored the structure of the heavens without leaving their observatories. Contemporary astronomers explore the most distant galaxies without leaving Earth. The instrument of exploration changes, but the fundamental impulse to understand what lies beyond ourselves remains constant. Looking at Proxima Centauri now, knowing that we'll never physically reach it, we can feel something other than despair. We can feel the profound privilege of living in an era when we can observe it, measure it, detect planets around it, and eventually understand it in stunning detail. We live in the first generation of humans capable of directly observing the universe. Proxima Centauri, invisible to the unaided human eye, is known to us. Its planet, Proxima b, was invisible to all of human history until 2016, is now observable to us. The distance that seemed to defeat us for 0.24 light years will become a distance we traverse with knowledge, if not with bodies. We'll send our understanding across that gulf through the medium of data and analysis. So we say goodbye to Proxima Centauri, not in despair, but in recognition. We acknowledge that your distance is too great for us to reach, but we celebrate that it is not too great for us to understand. We acknowledge the limit of human bodily exploration, but we embrace the unlimited potential of human observation and understanding. The cosmos revealed itself to us in the moment Proxima b's presence became known. Future instruments will reveal it further. We will explore Proxima Centauri through the only means available to us: observation, understanding, and the extension of human consciousness through technology. This is the future of human space exploration, not reaching the stars, but understanding them, not colonizing distant worlds, but knowing them, not leaving Earth for other planets, but reaching across the cosmic void to comprehend what dwells in that vastness. Thank you for journeying with us through this exploration of Proxima Centauri. Distance, human limitation, and cosmic wonder. If this deep dive into the mysteries of interstellar space intrigued you, please hit that subscribe button and turn on notifications for more explorations of cosmic mysteries. Drop a comment below, tell us what you think about the future of space exploration. Whether you believe humanity will ever reach another star, or what destination you'd like us to explore next. And if you appreciated this research, please give this video a like. The universe awaits our understanding. The journey continues.